everyone. Is this working? I can't hear. Okay. Okay, good. So I'm actually going to not go into too much of a technical detail. More than happy to share more if you catch me after the talk. I kind of want to keep it fairly light for sort of fairly wide range of skills. So I'm actually going to talk about the how we ended up rebuilding the ad blocker back in spring, actually, and well, why we did that. So if you're an engineer, as most of you are, you must be familiar with some variation of the problem-solving flowchart, and it kind of, the most important bit thing is, does the damn thing work? If yes, don't mess with it. Most of the other variations end up in this middle thing. The profanities are not mine, I pulled it off the internet. So it kind of boils down to this question of how much faster than an optimized native C++, which the previous AdBlocker version was written in, can you get? And sort of touches on this, does the damn thing work? Now, it turns out that the thing we had before was working. It was working pretty well, pretty efficient. It had some, clever Bloom filters and all that, written by some very smart people in the team. But our friends at Ghostery did a blog post, mostly sort of as a rebuke to Google's arguments about, well, all this way of doing ad blocking does not really work. It hurts the web performance too much. So they sort of did that as a rebuke to them. But they also kind of pointed out that, oh yeah, Ghostery is the best, leading, in terms of performance and all that. And in their post, that's a screenshot from theirs, with the highlight of mine, is that Brave is kind of an order of magnitude slower. Now we're talking microseconds here, so it's not adding seconds to your page load times. We're talking microseconds, but still, it's I would say embarrassing at best. So kudos to them, of course. They had maybe the methodology is not perfect. I don't think any of them are, but it's kind of very thoroughly tested and explained with Node.js as far as you can go with that. And they published the entire code and data set. So you can actually just run it, convince yourself that, yeah, they're actually not doing anything stupid just for the sake of writing a blog post. So, hey, good. So that's a good target for us to beat. And, well, the spoiler alert is, of course, that we did. So we beat our old version by something like 69, 70 times per request on average. The clicks was like off by 1 or 2 microseconds. So again, we're talking about that sort of level optimization for fun, if nothing else. And well, nothing else is probably a bit of an understatement. It's one of the core components in the browser, and every request gets processed by that. So you sort of need to be efficient around these things. Now, remembering the problem-solving flow sheet, we have a few basic requirements then, especially because we're actually doing a complete rewrite from an existing working component in something else. So the one we have already talked about is you need to be faster. Rust is fairly well positioned for that. You can actually write things that are at least as fast as C++, depending on how good you are with that. Now, it also needs to run within the core browser. So it's all C++, mostly, some C. So it turns out that Rust is very well interoperable with C, C++, with bindgen, very similar to WASM bindgen. We also happen to have a requirement that it needs to run on Node.js, partly because of some of our own tooling, partly because it makes it easier for other team members to debug some of the rules when the blocking works well, not so well, not because it's bugs in code, but because it's kind of bugs in the rule sets that are popularly used. And well, also because we actually still need to use the Ghostery's published code and data set to beat their benchmark, right? It's only fair to not change the rules of the game if you're actually trying to play it. And the important one, maybe unusual, is that it has to be sort of exactly as broken as the old one. So you sort of have to have this bug-to-bug compatibility, because sometimes things happen unexpectedly when you change things too much, even if in the correct direction. So there was a pretty non-trivial test base for the old one. You sort of have to port it over to the new one as well. Luckily, syntax of C and Rust is similar enough, so you can mostly do it with search and replace, then a bit of tweaks here and there, and then a bit of self-convincing that, yeah, this is actually doing exactly the same. So not completely automated, but relatively easy. And one thing where Rust really shines, in my view, is that, well, you should not be introducing new critical vulnerabilities, and kind of the safety really helps there. So, hey, Rust to the rescue. Of course, when we published a blog post about this rebuild back in spring, it caused a bit of a storm on Reddit and the Orange site, and I certainly did not read the comments, but most of them were sort of this whole discussion, oh, is Rust faster than C++? Well, it's actually more about the algorithms than Rust by itself. It helps. It really helps when you actually have a sense of environment to experiment, but the algorithms in this case was the major improvement because we completely changed how we're doing the matching. So as a very quick explanation of why ad blocking, the way it's done by most of the ad blockers today, is actually difficult. By the way, who actually uses Brave? Just curious. Okay, not so many. Who's heard of Brave before then? So we need to do more convincing. Okay. Who doesn't use any ad blocker in their kind of day-to-day web browsing? Okay, a few adventurous people. Okay. But a lot of them actually are based around this notion of filter lists that are publicly, that are maintained by the community, easy list, easy privacy being the most popular ones. And you have things like these, right? Fairly arbitrary syntax pioneered by AdBlock originally. The syntax doesn't matter that much, but you have a lot of rules. So you have, like on easy list alone, some like 55,000 rules. I think more by now. And all of them, with some quotes, need to be checked against every single request that's coming through the browser that you need to load. You need to decide whether or not you actually want this loaded or not. That means if you're actually trying to render a page at 60 frames per second, then you have 200-300 requests coming through in that time span, you have very few cycles per request rule combination. So that's why you actually need to be fast. This is why these microseconds matter. And it's also not a tiny part of this work that the browser needs to be doing, because in our experiments, something like 20% of requests on common popular pages get blocked. In some pages, of course, more, in some pages less. And what doesn't make it any easier is, of course, that this syntax is a bit crazy. You have substring matching, you have subdomains. So this, for example, says that, well, linkbucks.com needs to match when that's part of this URL. You have importance, so if a rule is matched important, you bail after match, like as soon as you match that, and like nothing else matters. If you have types, is that an image request type? Is it a script request type? You have not types, so basically anything apart from scripts. You have exceptions. The first one is actually an exception. Even if you matched any other rule, but you also match an exception, then actually you should be letting the request through, mostly because it causes web compatibility issues, something breaks on the sides. So that's kind of the way of solving it. And then, of course, things like arbitrary wildcards and whatnot. So the syntax becomes tricky. A lot of matching to be done. You need to be fairly fast. Now, how a request is matched, and it's actually fairly straightforward on that side. You have things like a host name, root domain, schema, the rest of the URL. You tokenize every single thing to essentially a number, because working with numbers is a lot faster than matching strings through a hash function. Hash function in this case doesn't need to be cryptographic. You just need to make sure that the collisions are fairly infrequent on similar strings, and you kind of choose the fastest one. There was a bit of an adventure with one of those two, where it was supposed to be cross-platform and very highly optimized, and it was very highly optimized, but yeah, on 32-bit environments, it was actually giving a different hash. Not the intended behavior, but you, as a developer, end up having to take care of that and make sure that these things work. And then, of course, the real trick is you take all of those rules, you also figure out which are the tokens. So kind of the simple logic there is, if something is linkbucks.com, both of these are separate tokens, and the request that matches that has to match both of these tokens. So you end up finding a list of tokens for each of them, putting them all in a hash map, finding which is kind of the most descriptive token for every rule, because essentially the most descriptive being the least frequent one, because you're always trying to minimize the number of rules. Remember I said you have to match every request against 55,000 rules. As best as you can, you're trying to avoid that. So ideally, you would only match against 50 rules, or like as few as possible. Some of those would be 5, some of those would actually even be 0. So kind of all about cutting down the search space. And this is where the speedup comes from. So being fair, Rust is great. Rust is not the source of your speedups. Maybe because you actually were able to dig in much deeper into the code and optimize it more aggressively yourself. So what about Rust then? Well, one thing is that I'm positively frightened of C++. And I actually feel that any sane person should be. It's really easy to, for me anyway, I don't pretend to be an amazing coder, to forget that, as you were passing this bit of memory from somewhere to somewhere, and especially you start working with bits and pieces of strings that you don't want to copy because copy is expensive. Again, microseconds. So all of these things add up. Memory reallocation is expensive. Copying is expensive. You want as few of those operations as you can, so you start really optimizing the tiny little things. And well, in C++, if you forget it, you get a seg fault, possibly in production. Maybe you get a critical vulnerability just because of that. To me, that's scary. Don't want to do that. And another actually thing that I really enjoyed when working with Rust is this, there's test-driven development in this case, because that was kind of the goal, part of the game, benchmark-driven development. So Rust, especially nightly, has this built-in tooling for benchmarking, for micro-benchmarking primarily. Every single little thing you can test, you work out your payload, you run through the benchmarks, you can monitor how much faster does it get. That's what I was doing with choosing the right hash function. That's what I was doing for the entire thing. Kind of the entire thing, you sort of end up doing micro-benchmarking as an integration test. A bit of a weird combination, but you can do it. I was using the criterion crate. Can talk about that a bit. Can talk about that later if you want. But it's a very neatly done crate that actually makes the benchmarking fairly simple. You just do cargo bench, runs through your benchmark, spits out the number. And the thing that really made my life easier is this very obsessive community. So probably the best thing about Rust is as the community is maturing. So one of the key things, because of all the string matching, substring matching, and all of that, is availability of good quality code. So you have the regex crate, which obviously was very important in here. And in there you actually have very advanced optimizations that come for free to you. So that one, especially since Rust, and I think something like 135, which is not a very old version, but has been around for a while, stable enough, you have SIMD optimizations enabled by default. Now, what the SIMD is, what most of your modern CPUs, some of them on mobile phones can actually do just like that. It's single instruction, multiple data. So it's parallelism that comes free. No thread synchronization, none of that. If you can actually pack operations in memory close enough to each other, with a single instruction, you can process 4 64-bit words and similar. So great, can actually have significant improvements there. Another example of that was, again, we rely fairly heavily beyond our kind of basic structure on hash maps. Turns out the default at that time, the standard Rust implementation for the hash map had a slightly different set of goals. So it had to be kind of much better balanced. And in memory, kind of some more DOS prevention. And some guy decided to port Google's Swiss table. Swiss table is kind of Google's version of a hash table, and that's kind of, again, very highly optimized for their workloads, but turns out to be working quite well in general. So he went there and implemented it all in Rust. Turns out to be working very well. Actually, turns out to be working so well that by now, don't remember from which version, but by now it's part of the standard. So it has replaced the Rust standard hash map. So kind of don't even need to be in most cases aware of this being the hash brown thingy. And then you have things like two-way crate, which gives you faster substring search when you're just doing simple substring search using this two-way algorithm, again, some SIMD sprinkled on top. So magic all the way, most of the stuff you don't need to care about. A lot of the stuff, by the way, happens to be the deeper optimizations unsafe, which then also means that you, in your own crate, can just say, well, forbid unsafe code. So I was actually not having to write any unsafe code. So again, goes back to my wish to offload a lot of that responsibility and say, well, a lot of people are using those crates. I'm just doing this kind of as the first production grade bit of code in Rust. I played around with Rust a bit, but a lot of that process of actually building this up was a learning process for me. And so yeah, because of that, you can just say, sweet dreams to the security team. The security review goes through smoothly. At least, the most bits that they really need to care about as kind of things potentially go wrong are taken care of by the compiler and the borrow checker and all that. So a good example, though, of an optimization, and that's where it starts getting a little bit funny in terms of how you do things with Rust, is we have this notion of very similar rules. So these are actually all real rules from the, I think, easy list probably. And all of them are kind of a combination of add, adds, and top. So very similar tokens, hashed to pretty much the same numbers. And if you, for each one of them, you look them up from a hash map, you fetch them, you start checking whether it's an actual match, like all this branch switching and all of that starts taking time. Now, what if you combine all of them? It turns out that this monster of a single rule as the regex matches a lot faster than all the individual rules. So just combination of that automatically based on kind of some flags in those rules, you combine them. Again, thanks to the regex crate, you have like on our benchmark, or more like Ghost Tree's benchmark, that alone from the base code was saving like 46%. That's a bit, it's one of these things where you run the benchmark and you go like, no, can't be. But yeah, fine, that works. So that was a nice one. And where it really helped is that, for example, the Rust crate, again, the regex crate again, has this notion of individual regexes that has this notion of regex sets. So what I ended up doing is putting together like an enum, where you have a single compiled regex, a compiled set of regexes, well, kind of, the regex and the regex set are coming from the regex crate types. These ones are kind of my wrappers for convenience and how you things around, how you pass things around, and how you not throw exceptions out, because in Chromium in general, there's exceptions are not thrown. You need to handle the errors more gracefully than that. And great, right? Except you have one of these catch-22 situations with Rust. Because Rust very strongly encourages immutable data, immutable types. And the AdBlock lists are computed and serialized offline. You don't want to be actually parsing every single rule in addition to all the matching you do when the request comes in. So you do all of that work offline, you serialize them, you kind of know that at least the data structures are already fairly optimal by that point, and you're good to go. Except that regexes is a thing that's, well, the regex expressions are clearly serializable. The regexes themselves, as a state machine that does the matching, not so much. So, but you don't want to be recompiling them every time when a rule comes in, because, well, that's relatively speaking expensive. And you can't save a compiled regex, sort of, lazy computation type of thing, because, well, everything is immutable. So you keep going through this catch-22 until you go like, there must be a better way. And that was actually a very, oh no. Great. So that was a very interesting pattern for me, myself, is this, and that's the only bigger piece of code that I'm actually going to show, is this notion of interior mutability. Now, what interior mutability means in the Rust book is a mutable borrowed to an immutable value. what does that mean for me, like in more human language, is that you're sort of lying to the compiler that that thing is immutable when actually underneath it is. And the API you provide to the user of your struct is an immutable one. They don't need to pass in the mutable reference to that same structure. For all they care, nothing changes there. And not an unpopular pattern in a lot of the Rust crates. Now, this is not the only way of doing, by far, doing the interior mutability. This was one that I liked. I found it fairly easy to reason about, and kind of got stuck with it. So the crux of this is basically you create a new scope to make sure that when things go out of scope, things get released. You have this, you borrow mutably this regex, which is a ref cell. This is a special type in Rust, which is basically is a reference cell to this bit of memory that's actually mutable. And as somebody described this is the bit that you're lying to the compiler, or at least compiler is willing for you to be lying to them. And then the kind of application logic type of thing is if basically this is what has already been computed, then you just return that. Like some unwrapping, cloning, and just kind of spit it back out. If it isn't, then you call your own function, this compiler regex, the dot. I just didn't want to copy paste all the arguments there. And you save those into your mutable borrow of cache as a new thing. And then you leave the scope and call yourself again, which will return. So what it actually boils down to is instead of directly accessing a field of a struct, you have an accessor method essentially, which does some ref cell borrowing. If it's already computed, just return that. If it's not computed, compute it and call it yourself recursively to return that. Kind of fairly straightforward, essentially one branch. Now, another weird optimization, though, is this thing with avoiding UTF. Now, UTF is valid in both URLs and AdBlock rules, and is not completely infrequent in either of them. Now, Rust is wonderful in that sense. UTF strings out of the box. This is kind of what, by default, if you're using str or string, this is kind of by default what you have. Except that where it can actually bite you. If you already have converted everything to ASCII because you want the same encoding for faster matching again, you have already converted things to ASCII, but turns out that if you actually just do, in this case, just kind of normalize URL to lowercase instead of URL to ASCII lowercase, that by itself, because this is done on every request, and we've optimized the matching bit already quite well. Now we're tokenizing the request. This turns out to be relatively expensive. So again, boom, 34% average saving time. So that was the kind of very funny bit of the journey, where basically you change one line of code or a handful of lines of code, and you say, boom, 40% savings, 30% savings, all that. Of course, I mean, so there were days where would spend 3-4 days just trying to shave off another microsecond because we're not quite at the target yet. So these are kind of the boring bits, but the surprising bits were things like that. So it's sort of, the lesson here is that it both helps you, but you actually have to go through your code line by line and think, right, is this actually doing what I think this is doing? So the takeaways for me, at least, were that there are a bunch of languages that are fast. Rust is great. C++ is great. I'm not trying to start a war on that. Algorithms typically win the game. And to be fair completely to others, the algorithm we ended up adopting is fairly similar to what uBlock Origin are doing, a popular AdBlocker, fairly similar to what Ghosty are doing. We're having a bit of a competition at that point where I was optimizing some bits here and there. They were optimizing some bits in their code. Or kind of, after the blog post, the race wasn't over. And I loved it, kind of a very sporty spirit there. And what I felt, at least, is that the Rust level of safety, memory safety, type safety, the borrow checker, even though the borrow checker is kind of, I wouldn't agree that this is your friend. It's kind of more of this very strict teacher that you had at school. Anytime you go wrong, it will shout at you. But eventually, when you get your head around this is a very, kind of becomes a very natural way of thinking about memory, ownership, and how things should be done in a safer way. Like when I go back to C++, I tend to try to use some of the same patterns, because if you just get a reference, you don't know who's owning that, you don't know whose responsibility is to clean that up, and things can get tricky. And yeah, surprisingly good interoperability. So with C, direct. With C++, a bit less so. You need to write some extra wrappers yourself. With the bind-gen crate, with Node.js, turns out to be, didn't go into those details, but it turns out that there's a crate called Neon, which, again, very similar type of code as with WASM. You just sort of annotate things here and there. You write a bit of marshalling to convert things between JavaScript, JSON values, and Rust, and you're good to go. And I actually also did a WASM version of that just to see, well, is it actually faster to do things between JavaScript and native kind of C type of thing, or between Node.js and WASM? And luckily, Node.js now supports WASM, but turns out to be, because in the end, the matching between requests and all the rules is actually so fast, the overheads of WASM in that specific scenario, not saying WASM is bad, WASM is great, were slightly higher than with C. So kind of this, again, funny name of the game where you kind of look at these tiny little details. I enjoyed it. And really great community. It's really great to see Rust maturing. You have really solid crates built up. You can actually really start pushing out production-grade code with the tools that others provide for you. So kudos to them. Couldn't have done that without all of that. And it's important, nevertheless, to have in mind that it can still be rough around the edges. So this ASCII little optimization was unexpected at best. There was another one with, I think I mentioned this in the beginning, where the hashing function was not exactly performing the same way on 32-bit environment as 64, even though the documentation said that it did. So don't just rely on the documentation, test, test, test. And so yeah, that's kind of the journey. We're more than happy to share more. Thank you.
Any question? Yeah.
Thanks. Yeah, it looks like it works. I've got two questions, actually. One of them, what are the most useful profiling tools? And the second is, did you validate your dependencies at all before going one way or the other, or deciding on the end product?
The second one is a bit easier. So yes, as in kind of mostly a sanity check. You go to GitHub, you see who's the developer, you see how well it, like, is it a live library? Because it's an open source community, things happen, things get abandoned because other things get in the way. Like with the specific hash function, didn't do enough. That bit me back, and that was hard to change after you actually landed in nightly. So made some mistakes there, but highly recommend validating. And I can see now in the community, there's kind of more efforts to have this shared validation that somebody verified. I forget the name now of the project where kind of you sort of have a community type of code review, which I think is a great effort. It's always a problem with these library-based communities where you essentially have the package manager built in. NPM has a lot of the same problems. Rust has a lot of the same problems. Maybe not as bad as NPM just yet, but these are fundamentally hard. Having cargo on by default, I would say, is one of the biggest strengths of Rust. And it actually makes it a lot more smooth. It makes it a lot easier to keep up to date with your dependencies and all that. Of course, it's not perfect. It's always a trade-off. Does that make sense?
Yeah.
And so about profiling, mostly system standard tools. So for kind of actually to look into what was still taking up a lot of time, like memory reallocations, because you're kind of off by one by pre-allocating. I was just using Apple's instruments. and kind of the memory profiling tool there. I mostly work on macOS kind of as a daily driver, so that was working pretty well. All the symbols were recognized, and even in release mode, of course, if you compile in release mode to have all the optimizations on, you kind of only have the stack trace level of information. But if you understand your own code base, you at least know that kind of whereabouts in the stack things are not happening, or like spends most of the time or uses some memory and so on. So that's kind of the simple approach that I was taking.
Yeah, that makes sense. Thanks.
Almost.
Hello. You mentioned that Rust itself didn't really make it much faster with the algorithms you were using, but were there any algorithms you were able to directly implement specifically because you could trust Rust not to break things in the way that maybe C++ might? And as a result, Rust directly resulted in you having a speed performance boost.
I mean, it's one of these things where it becomes this argument of, you know, was I a better C++ developer? Would I have not been able to do that in C++? Kind of tricky. If you spend enough time on any of those, you can probably do it. I found that especially this substring matching, patching, moving things around and squeezing them down, that was kind of you know, the notion of slices, especially in Rust, and the notion of substrings and kind of passing things by reference there, that made my life a lot easier than as if I was doing that in C++, but that's kind of, it goes too much into personal preference territory, I would say, than you know, to actually say that, oh yeah, Rust actually wins hands down there. I liked it better, but yeah.
You kind of alluded earlier to using macOS as a daily driver. I guess it was mostly a CPU-bound problem, but did you notice any difference in cross-platform performance?
Tested a bit on Windows, on Android. So, as in, if we noticed the difference between the old one and the new one, yes, across all the platforms. In terms of whether it was between, let's say, Android and macOS, yes, because the Android devices typically have a lot, you know, less powerful CPUs than this one. So again, this, as you say, this was a very CPU-intense problem. Not a huge workload, but the bottleneck was the CPU. There was some memory reallocations that were expensive, but kind of the faster your CPU goes, the faster the overall things run. So didn't actually have, like, you know, completely identical hardware between the different platforms we tested on.
You already answered the question about optimization, but can you explain maybe a little bit more like the process? Like, did you took like the C++ version and then analyzed it and see like what you can optimize, then write the Rust version and then continue on that? Or like, how did you work? And like, for example, the 2 ASCII lowercase, how did you find out that?
The two which ones?
The 2 ASCII lowercase function.
Oh, yeah.
How did you find out about that?
The second one, I don't remember the actual process. Like, it's one of these things where in the profiler, you look at where you're spending significant time, and it happened to be around this, you know, tokenization bit where you're just taking in the request and start manipulating it to extract those tokens. And then you start going through the code line by line and thinking, right, it can't be here, it can't be here, it can't be here, it has to be somewhere. Then you do another loop. And then oftentimes the suspect is where you're not just doing a simple operation, but you're calling some other function that's written by somebody else. So you look at any functions that you're calling and say, well, okay, what does this function do? What are the alternatives? Does actually replacing that with something else with simple requirements, the requirement not being, you know, UTF support, make any difference? It does. Yay, hooray. So that was, if I was trying to repeat the process, I would probably follow the same. I don't remember if I was actually doing that exactly this way, but I suspect that yes. And could you remind me the first question?
Did you start from the C++ version?
Oh, yeah. No, I threw away the C++ code. So I basically looked into the competition that were allegedly beating us and started looking into, right, so what is it that they're doing? Our algorithm, I would say, made sense at the time that it was built up because the kind of it wasn't. It's a few years old. The whole ecosystem, in my view, is actually getting worse. So there's a lot more trackers on every page that you have now than you had, let's say, 5 years ago. So this notion of Bloom filters intuitively makes sense. You sort of have thing coming in, you tokenize it, you check. Bloom filters are basically meant to very quickly tell you that, oh, this thing is not in the set of things you should be checking. And off you go. It turns out that in reality, a lot of these requests, you need to go in and check against the specific rules. So that was kind of, I would even say that this is probably what changed between when the old one was written and this rewrite. But that was, no, I'm actually mostly inspired by the competition, like really going in, analyzing that. I pretty much prepared a slide deck of how the alternative algorithms work. We discussed with the team, oh yeah, we should actually patch it up. And it was kind of a funny conversation where with the team lead, we go like, so should we do it? Like, yeah, we could. Or maybe the engineers should do it. I'm kind of more on the research team. And we know that the engineers are overloaded with the backlog of their own. So like, right, maybe we should do it. So how should we do it? Should we actually just improve the C++ version? That conversation happened, or just throw it away and do it from scratch. I'm like, how about we throw it away? That's more fun that way. And then there was a conversation, so what do we write it in? Well, C++ is good, but I don't want to do C++. So how about we do it in Rust? That's kind of this arbitrary thing. What really helped in my case, not necessarily universally true in all organizations, is that there was already a fair bit of support for Rust. Like there is another couple of components in the browser already running with Rust. Some of the core engineers actually really are fans of that. The founder, Brendan Eich, was previously in Mozilla, so kind of some obvious reasons why Rust has some more support too. So kind of the cards were stacked in my favor in terms of convincing the team that this is the right way. And I got the learning opportunity. So great.
And anyone else?
Hello. Cool. Hi. Yeah, this question has nothing to do with Rust per se. I was just interested about how blockers and trackers work. Do you have a sense?
It's really echoey.
Oh,
Could
sorry.
you do a bit slower?
I'm just interested about your blocker. Do you have a sense of how much it blocks, or if I use uBlock Origin, how much crap kind of gets through if you're just browsing in a normal way?
I would say like between uBlock Origin and Brave, this is kind of probably the aggressive one. So we really try to kind of keep up with the game, and we are funding Ryan Brown, who's one of the core maintainers of EasyList as well, to make sure that he has the resources to keep doing the good work. So in that sense, it's a community effort. So both of them, in terms of blocking, are doing pretty similar. In my view, our core benefit is actually that we are within the browser rather than just an extension, so we don't suffer from some of the overheads. We can actually catch things a bit earlier. Plus, there are some additional like fingerprinting protections that we have in terms of actually blocking things that are not strictly a tracker or not necessarily caught by the static list, but something that seems to be doing something dodgy. So, not a very direct answer. The evaluation of these things is pretty hard. It depends on the individual user browsing behavior. It depends on how fast some of these sites and trackers are changing. And like I would just sort of highlight, it's not the ads that are a problem in our view. It's the trackers. That ecosystem is completely broken. The ads is sort of, you could say it's a necessary evil, but they don't really have to be evil. But the trackers are really making it bad for the publishers, for the users, for the browsers, for the overall experience. So we're in that fight. And we're in together with our comrades at Ghostery and uBlock Origin and all that.
Okay, last question here.
So actually, something I was curious about is when making a production system, you mentioned you had a pretty large and extensive test suite that you had to port over from C++ to Rust. What was your experience kind of doing that porting? Did you feel like there were things that were missing, or did you feel like the experience was better when you ported it over to Rust? Was there anything that you think that should be provided but isn't currently provided by Rust or the surrounding packages?
I think it's one of these things where, especially for something like Rust, just having more and better interoperability between those kind of different primary languages would be nice. So maybe it would have been even better if I didn't have to port them over, but actually just run them against essentially the binary compile thing. So that would have been great. That would have, given even more confidence that the whole thing is working exactly as it was working before. Now with the port, you always can miss something. You can kind of change the meaning maybe here and there. But on the other hand, it did help me catch a couple of bugs that I more like omissions in my logic, because the logic completely changed. We threw away the C++ bit. But the tests and the cases that you have accumulated over time still have to match up. So better support for that, I think, would be great. I haven't had a chance to play around. Oh, and looks like don't remember the name now. There is a kind of new approach to the C code generation from Rust. Kind of supposed to be, yeah. And so looked amazing. Haven't had a chance to play around with that. I think more efforts like that can only make things better. Okay. No, but I mean, I think having some wrappers around C in C++ is a bit of an easier step, especially for things like testing than going from Rust to C. So if that thing is working well, then that's good.
Okay, thank you very much.